we got very, very lucky. There is indeed an owner's manual, operator's manual, that is on the website for OptoElectronics. And in that manual, which is a PDF file, they do have a schematic. Now what I've done is the schematic is spread over 2 pages, boom, boom, and there's actually more down here which I'm not showing. I have taken the salient portions, stitched them together here, and what I want to do is I want to explain to you what's going on, but now that I see what's going on and the switches, I understand why I wasn't getting voltage on certain sections, and that in a nutshell has to do with the fact that this is a battery powered device. So what they're doing is, if I have those buttons set to a particular configuration where certain sections are not being used, they actually shut down power to those sections so as to conserve the batteries. So the fact that I was unable to get 5 volts at certain portions may not be a defect. That may be planned, and I'll have to reconcile the voltages when they're on and when they're off with the switch settings to make sure that they make sense. But what we can do is go through this schematic to understand what's going on with this thing. This up here is just the power conditioning. So over here you have from the power dongle anywhere from 9 to 14 volts pulse DC. It's going here, being smoothed out with a 47 microfarad capacitor, and then it's going to this regulator chip. These here are the NiCad batteries, the 4 NiCad cells in series, and this here is a charging circuit that would charge those cells when the unit was not being used. So this switch would be in this position when the machine was off, so that the charger circuit would charge up the cells. When the machine's being used, it'll either be driven by these cells to the 5-volt bus, or would be driven by this circuit over here, which would also recharge the battery. So if, boom, the power switch is on and you're getting juice in here, boom, it'll charge the cells and run the machine. This here, I don't recognize this as being part of this device, and actually I'll show you when we get back to the device. It looks as though there were 2 versions of this frequency meter. There was one, the one that we have, which is probably a more budget one, which uses the crystal oscillator exclusively, or there was probably a more expensive one that had a switch you could flip and you could feed it a calibrated 10 megahertz, which would be far more accurate than the crystal oscillator that is not oven controlled. So this piece here is in dashed lines because it doesn't apply to us. It doesn't apply to all the models. So we're going to omit this. This down here, this is the 7216. This is the 28-pin chip. And the portion I have omitted are the LEDs down at the bottom here. And these are the segment drive digits. Or I'm sorry, these are the segment drive circuits right here. And these are the digit strobe wires. I didn't show all this because we know this is working, so I don't have to concern myself with this. These are all the switches that will control where the decimal point is going to be and whether or not leading zeros are going to be truncated. So I will show you that when we get back to the device. But this here, and this here, and this here are what we want to concern ourselves. So let me give you a tour of what this is, because they've done a very nice job of segmenting the schematic, organizing it into component functions. And what I'll do is I'll use some color coding here to show you what's going on. So let me call this up. The purple area over here, this we know is all working. This is the intercell chip. We know it's working because it's driving the LEDs. This green area here is the oscillator, the 10 megahertz clock signal that's going into the intercell chip. We know this is working because both the gate is working, and those LEDs are being strobed. This here, this aquamarine section here, this here is the the gate LED. We saw it blinking on and off, either one time a second, once every 10 seconds, or blinking on and off feverishly because it was gating at 1/10 of a second. We know this LED is working. It's being driven by this PNP transistor over here, which is being driven by the intersilk chip. So we know this is working. We know this is working. We know this is working. The areas we don't know whether or not they're working are this, and this section all over here. And this orange section here is the one I'm most curious about. Let me explain to you what's going on. This here is the input for the highest frequencies. This is the 50 ohm input, and it'll go all the way up to 600 megahertz. This section here, we don't have to worry about. This is all preconditioning. I mean, if it proves to be faulty, we'll have to worry about it. But right now, in terms of explanation, just consider it simplifying that it's signal conditioning. Here are your clamping diodes, one up, one down, meaning that this is preventing you from putting in too high a voltage, an AC voltage. This will protect the rest of the circuit from too high a voltage, positive, too low a voltage, negative. This here is where you're getting your 50 ohms input impedance. And this here is that 650 megahertz prescaler that we saw from Texas Instruments. So this here is where the 600 megahertz is being divided by 10 before being shoved over to this section over here, which we'll get to in a minute. This is the other input. This is the 1 mega ohm impedance, and they're claiming here that it'll go all the way up to 60 megahertz. Again, we got line conditioning here. There are your clamping diodes right there. And these three stages were in that integrated circuit that was the no, it was the line receiver. There they are. There are those three gates, and those three gates are being used for conditioning, signal conditioning. Remember, the system doesn't know what kind of garbage you're going to send in over here, so it's first going to protect. There's an FET transistor, high input impedance, voltage driven rather than current driven. It's almost in a Darlington configuration with this PNP transistor. Then you have these three, these are comparators that are in that package. So all three of these are in this one integrated circuit, driving this transistor here, which will be used. I'll show you later on how this section works. But the point is that here's +5, and you see that this section is not always powered. It's only powered when this switch is in this position. When this section is not being used, meaning that you're sending your signal through the 50 ohm input, you're not going to be using this section. So why power it? That'll just drain down the batteries for no reason. So the switch here flips this way, powers up this circuit. You see the 5 volts can either go to this circuit or to this circuit. Only one of them is going to be alive at any one time. Now, let me take you through the signal paths more precisely. Let's start out with this one. So, at your lowest frequencies, so now we're talking frequencies below 10 megahertz. Remember, this chip can handle up to 10 megahertz with no divide by 10s necessary. So if I have a signal that's below 10 megahertz, it's going to come into this area here. It could be garbage signal. It could be, noisy, have all kinds of bumps on it, that kind of thing. This section here is going to convert whatever garbage comes in here into a nice clean clock pulse. And then it's going to go through this path to this orange section, which is the final driver. Pin 28 is the clock input to the frequency meter, the frequency chip, the intersil chip. By here, it's going to be a nice clean square wave pulse coming in. And that's, here's 5 volts, boom, coming in through this resistor. And this transistor here, this NPN transistor, is basically grounding this side of the resistor, knocking this down to 0, or if this is open, not conducting current, then we're getting 5 volts, boom, through into here. So at your lowest frequencies, you're going through the conditioner, coming right up here, and this switch here is where you're telling it, hey, we've got a very low frequency, so we do not need to go through this 74196 divided by 10. We're just going to bypass it, come around here, come in here straight into the chip. Now, if I have a frequency coming in that's more than 10 megahertz, but less than 60 megahertz, what happens next? Now, we're still using this section because we're still using the high impedance input, and we're still doing the conditioning. But now this switch, instead of being up here like this switch now is coming down here. So now we're coming out of the conditioning circuit into this divide by 10. The divide by 10 now, and this switch is ganged with this switch. Boom, this one's going to come over this way. So now the output of the divide by 10 is going to come in here and drive the pulses. So if I have a 60 megahertz signal coming in here, it gets cleaned up to a 60 megahertz square wave. It comes into this divide by 10, and this is transistor. So this is expecting a clean square wave in. And what this chip, beg your pardon, what this transistor here is doing is actually converting the output of these comparators. It's converting it into a TTL compatible driver with the proper output impedance necessary to drive the TTL circuitry of the 74196. Remember, these are high frequency. TTL logic was high frequency in those days, but it was very power hungry. Drew a lot of current. So that's why this transistor is in here. And so then we're dividing by 10. So if we have 60 megahertz coming in here, we're coming out of this chip with 6 megahertz, which is digestible by the intersil chip. So we're good. We're good. Now, if we have a signal that's more than 60 megahertz, we're going to be using the 50 ohm input circuit. Again, we're just going to be conditioning over here, just cleaning up all the garbage of the signal, converting it to a square wave. This here is a divide by 10. This is that 650 megahertz prescaler by Texas Instruments. It's going to knock it down by a factor of 10. So if we have 600 megahertz here, this is going to knock it down to 60 megahertz. So we're going to pass 60 megahertz down through this path into this divide by 10, which is going to knock the 60 megahertz down to 6 megahertz into here, and boom, the intersil chip can handle the 6 megahertz. So what the intersil chip is going to do is it's going to present 6 megahertz on the digits. But remember, the chip here does not control the decimal point. So it's just going to put up 60000, whatever it is, and now these switches are going to adjust the location of the decimal point so that instead of appearing as 6.000, it's going to appear as 600.00. In other words, these switches are, that's where the intelligence is that tells the LEDs, hey, we've divided by 10, we've divided by 10, so we've divided by a total of 100. That decimal point needs to slide over by 2 digits. So this brings us to a head now. No matter which input I used, and no matter what button combination I used, nothing was changing. I was just coming up with zeros on the display. So if you'll notice, this path all goes through this orange section. This path, vroom, all goes through this orange section. This path all goes through this orange section. So I am strongly suspecting this NPN transistor right here is probably on the fritz. It could be a resistor, but keep in mind that if it's this resistor over here, that's not going to explain how the very low frequencies are also being affected, because quite frankly, those are just coming boom straight through here. So I suppose it could be this, could be the transistor, could be this, although I doubt it's this. The point is, whatever it is that's the problem, I strongly suspect it's this, because no matter which path the signal takes, it all funnels into this section here. So if there is a single point of failure, it's probably in here. So I'm going to take a look at this transistor to begin with. So let us go back to the device and have a look.